Hello, everyone. So thanks for tuning in. So I'm going to speak on uniform brackets, containers, and combinatorial Macbeath regions. So this is work in collaboration with Arijit Ghosh from the Indian Statistical Institute and Shay Moran from Technion and Google Research. So it's a tale of three structures. Firstly, we have containers from the area of online and distributed learning theory. Then we have combinatorial Macbeath regions or Mnets from computational geometry. And finally, we have uniform brackets, which sort of unify both the previous notions from empirical processes and statistical learning theory. So containers were recently proposed by Braverman, Cole, Moran, and Saxena. The idea is that, let's say you have a probability space which has a ground set X and a measure mu, and you have a family of measurable sets that you're interested in and a parameter epsilon. Now you want to approximate your family H by another family C such that for all F, which are member of your first family, there is a member G in the second family, such that F is contained in G, and the measure of the difference of these two sets is at most epsilon. Right, so then we say that the second family C is an epsilon container for H with respect to the measure mu. So Braverman et al. Were actually interested in the case where X is a set of endpoints in RD, and the family H is all possible subsets of X, which can be generated as intersections of X with half spaces in RD. And the measure mu is just the empirical measure or the counting measure. So what they showed was that for any epsilon in 0 and 1, this family has an epsilon container of size at most order of d by epsilon to the d. Now, in fact, you can forget about mu. So you can say that this is in fact a distribution-free bound. So this notion was inspired by containers for independent sets in hypergraphs, which has led to a lot of progress in extremal combinatorics and hypergraph theory in the last decade or so. And Braverman et al. Proved their bound using a new dual form of Carathéodory's theorem. And this led to improved protocols for bounding the communication complexity of distributed learning problems, such as learning of half spaces and linear programming. Okay, so let's move on to some discrete geometry. We have this beautiful theorem of Macbeath. Let's say we have a convex body in d-dimensional space. Then this theorem says that you can get a collection of subsets of the convex body such that, suppose you have a parameter epsilon, then any half space which intersects the convex body in at least an epsilon fraction of the volume of the body, there must be a member of this collection which is lying completely inside the intersection. Okay, and the volume of this member is at least a constant fraction of the volume of the intersection. But this constant doesn't depend on the convex body or on epsilon or on the half space and so on. Right. So this is the theorem of Macbeath, and it was proposed in 1952, and since then it has become a classical theorem in convex geometry. And so these collection of subsets, these subsets are called Macbeath regions, and this theorem has found applications and variants in discrete and computational geometry. So it was natural to think of a combinatorial analog of Macbeath's regions. And this was proposed by Mustafa and Ray in 2014. What they said was, so putting it again into this probability theoretic framework, let's say you have a probability space and you have a collection of subsets that you are interested in, and two parameters, lambda and epsilon in 0 and 1. So we want to approximate H by another family M, such that for any member F in the first family, which has measure at least epsilon, there exists a member of the second family, which is completely contained in F, and the measure of this member of the second family is at least an epsilon, is at least a lambda fraction of the measure of F. Then we say that M, the second family, is a lambda heavy epsilon Mnet for the first family H. Right, so Mustafa and Ray proved upper bounds for the size of epsilon nets for several geometrically defined systems. And the results were later generalized by Dutta, Ghosh, Mustafa, and Jordu, who proved that given any epsilon, you can find epsilon M nets for set systems that are semi-algebraic and also have VC dimension at most D. For some fixed lambda, so these are lambda heavy for some fixed lambda, and typically lambda is less than half, but it could be as bad as 1 by d to the order of d. So we saw two of the definitions. Now let's move on to uniform brackets, which come from empirical processes and learning theory. So here we have again a probability space and a family of measurable sets and a parameter epsilon, and we want to approximate our family H by another family B. And here the condition is that for every member F in H, there exists two members A and G in B, such that A is contained in F and G contains F, and the measure of the difference of G and A is at most epsilon. So if such a family exists, then we say that this B is an epsilon uniform bracket for H. So the epsilon bracketing number is just the minimum size of an epsilon bracket for H, and the bracketing entropy is the logarithm of the bracketing number. So it was natural to ask what is the most general condition for a set system to have a bounded bracketing number or container family. And you can see that this is not the bounded VC dimension because of result of Van Handel, which says that there exists set systems of VC dimension 2 and yet having unbounded bracketing number. So bracketing number is a strictly stronger condition than VC dimension. So this is a fundamental notion in empirical processes and statistical learning, because it gives, if you have bounded bracketing number, you can get simpler and more robust proofs of very important properties like strong law of large numbers, and as well as uniform convergence properties. And these proofs do not require techniques like symmetrization or assumptions like IID sampling and so on. So that's why uniform brackets or bounded bracketing number is a fundamental notion in empirical processes. So very recently, it has been used in the smooth analysis of online and differentially private learning algorithms by Hattalab, Roughgarden, and Shetty. So there are some connections that are relatively obvious between brackets, containers, and Mnets. So if you have epsilon uniform brackets, clearly you have epsilon containers, and also you have 1 minus order of epsilon heavy Mnets, right? So this direction is clear that brackets are stronger than containers as well as Mnets. Also, if you have Mnets and you have containers, then you should have brackets. Intuitively, this should hold, but we need that lambda should be very large, should be close to 1. But as we saw in the proofs of Mustafa and Ray and Dutta and Ghosh and Mustafa and Jagtu, lambda can be pretty bad and is definitely less than half. So there is a third point, which is that if we are looking at the specific case of points and half spaces in D-dimensional space, then notice that the complement of a half space is also a half space. So let's say you have a set in your set system, in your collection F. So this is a half space, and the complement is also defined using a half space. So you have a container CF for your set F, right? Now, since the complement is a half space, you have a container for the complement as well. Now, if you look at the complement of this container, the container for the complement set FC, then this complement is contained in the original set F, right? Which means that you can take the family of containers and the family of complements of containers, and this will give you a 2 epsilon bracket for the original family of points and half spaces. Or you can think that epsilon by 2 containers will give you epsilon brackets. Okay, so with all these observations, what are the new results? So the first result is that you don't need Mnets as well as containers to get uniform brackets. You just need one of these, and you need that this should hold for both the family as well as the complement family. So here the complement family is, take each member of your family and complement it with respect to the ground set. Okay, so en route to proving this equivalence theorem, we got several other results, like Mnets. If you have them for a fixed epsilon naught and a fixed lambda naught, then you can get Mnets for all epsilon and lambda. And also, if you have Mnets for a family, then you can get containers for the complement family, and vice versa. So with using this equivalence theorem, we were able to port the bounds, the known bounds on Mnets to the case of containers and uniform brackets. Right, so this gives us improvements in distribution-free bracketing number bounds for different set systems. So in particular, for the system of points and half spaces, we get a bound of 1 by epsilon to the order of d. So this is in d-dimensional space. And more generally, for semi-algebraic systems, we get again 1 by epsilon to the order of d. But here d, remember, is the VC dimension. So we also get lower bounds on these systems. So in fact, for points and half spaces, we show that you cannot do much better than 1 by epsilon to the d by 3. So there are there are sets of endpoints such that there is no Mnet, or there is no uniform bracket of size less than 1 by epsilon to the d by 3. And similarly, for points in hyperplanes, you can get a lower bound of 1 by epsilon to the d. So we have constructive lower bounds now. And as a result of improving the upper bounds, actually, we get improvements in the results of Braverman et al. As well as Haktalab et al. So for example, we show that the communication complexity of learning half spaces is order of d log n, and the communication complexity of learning convex set disjointness is order of d square log n. And again, now if we look at the smooth analysis of online learning algorithms, then again we get improvements in the bracketing numbers. So this is, let's say you have the class of degree d polynomial threshold functions in Rn. We can show that this class has bracketing number which is at most 1 by epsilon to the order of n by d. And similarly, if you take the class of k polytopes, you can get 1 by epsilon to the order of nk. Right, and these are improvements on these previous bounds. So previously we had instead of 1 by epsilon, we had n to the d by epsilon in the first bound. And in the second one, we had nk by epsilon. Okay, so now these improvements in the bracketing number give you also improvements in the regret bounds for the smooth analysis of online learning algorithms against adaptive sigma smooth adversaries. So I will just let you read these bounds. So in particular, you can observe that this log factor, log of the VC dimension, has been removed from the upper bound. And this is true for both these classes, P and D, as well as Q and K. So here again, we had log of the VC dimension. This has been removed from the upper bound. Okay, so here's some high-level proof ideas. So the idea is we will proceed in the direction of assuming that the complement set system has Mnets and trying to prove that this implies epsilon containers for the original set system. So there are two parts to the proof. The first is we get epsilon containers for sets whose measure is close to epsilon. So these are the small sets. And the second part, we use these small set containers to get epsilon containers for the entire set system. Okay, so let's take a member F in the family H, and let's see how we're going to get a container for F. So the idea here is we are going to extract a large chunk from the complement of F. And we're going to do this recursively. So every time we keep doing this, right? So now you can see that the measure of the complement of F has gone down by a lot. So we keep doing this delete and recurse idea until the measure of the complement goes below epsilon. And so the only question that remains is how do we get a large chunk in each round? So we want a large chunk from the complement. And the answer is, of course, that we will be using our assumption that the complement set system has Mnets. So let's say we take a lambda heavy epsilon by 2 Mnet for the complement system, and this Mnet has some sets which are M1 to MR. So for each I, what we are going to do is we're going to recurse on this reduced set system. So we delete the points in Mi. Then we look at the reduced set system, and we keep doing this. So at every step we branch on the size of the epsilon, on the size of the Mnet, and we do this recursion step until the measure of the complement becomes at most epsilon, right? So we get a recursion tree where the branching factor will be controlled by the size of the Mnet that we are getting, right? And for each leaf level node of this tree, once we reach a leaf level node, we are just going to add it to the container set, right? So in one step, what is the reduction that we get? So suppose you started with a family which had measure mu I, or rather mu of fi complement, then what you can show is that the reduction that you get will be at least something like 1 minus lambda by 2. So this is by assuming that the complement set has measure at least half. Right. So what is the maximum number of recursion steps that we need to go? So this is controlled by saying that we want the final measure of the universe or of the complement set to be at most epsilon, right? So this gives that the maximum number of levels that you go in your recursion tree is going to be something like order of log 1 by epsilon divided by log 1 minus lambda by 2. Right. So what is the size of the container family that we get? So it's the branching factor raised to the number of levels, right? So the branching factor is like 1 by epsilon to the d, then we get epsilon to the minus log 1 by epsilon. So this is much worse than the lower bounds and also the previous bound for points and half spaces, because there is a log 1 by epsilon in the exponent, right? So, but if we have that the original set F had small measure, then this is good. So why is that? So it's because let's look at the ratio of the complement to the entire system. So it's going to be this, the mu of the complement of the set. So this is at least epsilon. So this is again at least epsilon. And this, note that this is at least is around epsilon by our assumption, right? So we can show that this ratio is at least half always. So at each step, we can take a half Mnet, right? And now the size of the container family will be like, instead of 1 by epsilon to the d, it will be like 2 to the d. And now we can control the final size that we get. So it's polynomial in 1 by epsilon. And now we come to the second part. So here we want to remove this log 1 by epsilon that we were getting earlier in the exponent. So the idea is that we'll use delta coverings of set systems. So what is a delta cover? So it's a subset of the family that we are looking at, such that for every member F in the family, there exists a member in this subset, such that the measure of the symmetric difference is at most delta. So if we think of our sets in the family as characteristic vectors, then here's a typical family represented in the Hamming space or the Hamming metric. And now when we are taking this delta cover, basically we are saying choose a point, and you cannot choose anything that lies in this delta radius of this point, right? So, and further, you're saying that every point in the original family lies in this delta ball of some point in the delta cover, and that's why it's called a cover. So Hausler proved this bound in 1995. What he said was that if you take any set system with bounded VC dimension and any delta, then the set system will have a delta covering of size order of 1 by delta raised to d. So observe that we are basically looking at the space of characteristic vectors of sets in the set system with respect to the Hamming metric. So our goal now, in order to get containers via minimal coverings, our goal will be to get 1 minus order epsilon heavy Mnet for the container family, for the complement family, sorry. So let's take a minimal delta covering. Now for each set in the complement family, for a fixed set in the complement family, let P be the nearest neighbor of this set. And now, using a little bit of set theory, what you can show is that if you take two sets, two subsets, and they have small symmetric difference, the symmetric difference has small measure, then the intersection will have large measure. Right. So if we condition on this nearest neighbor P, we get that the conditional measure, which is like the measure of the intersection divided by the measure of P. If this is large, since this is large, since we know that P is the nearest neighbor of F complement, so that the symmetric, so that the measure of the intersection is large, right? And so we can also say that the measure of the original set F in this conditional space will be small. Right. So now, suppose we look at all those members F whose nearest neighbor was P. So we have these sets F1, F2, F3. Now look at the complement sets, right? All of them are very small. So what we are saying is all these small complements can be actually captured by an epsilon container CP, right? So we have an epsilon container which will contain each of these complements which have small measure. And we can do this because we already have a bound on epsilon containers for sets of small measure, right? And note that the complement family of this container is a 1 minus order of epsilon heavy Mnet for the set of the collection of sets in the complement system whose nearest neighbor was P. Right. So now remember that this was our goal initially. Like we said that we want a 1 minus order epsilon heavy Mnet. Right. So now we have such an Mnet, but only for the sets whose nearest neighbor was P. So we just need to take the union of all these families over all P in the covering, and this will give us a 1 minus order epsilon heavy Mnet for the complement family. So what is the size of once we take the complement of this heavy Mnet, this will be an epsilon container for the original family, right? So we have an epsilon container for the original family now. We just need to compute the size. So the size is just the number of members of the covering P times the size of the container family for each member. So we already showed that the size of the container family is like order of 1 by epsilon to the d. And the number of container families is also not very large. It is, you can choose delta so that this the number of members of P become of the order of 1 by epsilon to the d at most. So this gives you that the total size will be like 1 by epsilon to the order of d. So with this, I conclude. Thank you for listening, and I will be happy to answer any questions.